So it's my great pleasure to introduce our first speaker, who has been my mentor for many years, and one of the first people who was teaching me about tensors. So I am very happy that we can have here Jarek Buczynski from Polish Academy of Sciences, who will tell us about border apolarity. You don't need?
No, I don't need. I have my own. Thank you very much. Thank you for the invitation to speak here. The topic I'm going to speak about is joint work. Well, at least the new achievements, not so new anymore, but the new achievements are with Weronika Buczynska. And before explaining the border apolarity, I would like to spend some time on explaining the just apolarity without border. So in order to do that, my setting in these talks will be the space of tensors, which I will always denote by W, and it's going to be a tensor product of symmetric tensors of various degrees. Maybe. And each of these guys is a space of symmetric tensors in the vector space AI, A1 of degree D1. So each of those guys is a subspace or A1 D times. Just a space of invariant guys. I will try to explain why I use these brackets in a little bit, but for now let me tell you that I'm always working over an algebraically closed field, so complex numbers if you prefer, but this could also be positive characteristic field. And now I have to figure out if this works. Okay. So whenever we have a tensor here, the question people ask is how to write it in, well, some people ask how to write it as a sum of simple tensors. So what are simple tensors? The simple tensors is the set which I will denote by x hat, and later with x under some simplification. It's a subset of the vector space of tensors, which consists of the sets of those tensors that can be written as A1 or x1 to the power D1 tensor, xk to the power dk. So the simplest possible tensors. Each of those basis vectors are, each of those vectors is in respective vector space, and well, I guess that's more or less it. And in a minute, I will always restrict to a projectivization of this W, which means simply the space of tensors with 0 kicked out and be divided by the multiplicative group of K. In the case, this is just, if K is just, as a group is just the set of invertible elements of K. And in this case, this is because of that, I guess. So in this case, I will consider X as a subset of this projective space, and then this is isomorphic as anything essentially, but as a variety or as a set to the product of projectivizations of each factors. And so roughly what you do is you take the simple tensor like that, and you associate to it so a guy like this. Becomes a collection of classes of x1 up to xk. Classes modulo the equivalence. That's an element here. So the reason I'm discussing this in this way is because of the coordinate ring that I would like to introduce, which is I call it Cox ring for some historical reason, but it can be also thought of as a multi-homogeneous coordinate ring of X, which will be a polynomial ring in variables which I call alphas let's see, A1 up to, well, there will be many variables, so there will be variables that are called alphas, and they will correspond to the vector space A1. There will be variables that are betas, and many more, and then finally those that correspond to the final. So imagine there is k minus 3 alphabet letters between beta and gamma, and then we will have AK. So this AI, the lowercase ai, is just the dimension of the vector space AI. So for each vector space that I have, I get that many variables, and each of them has also some grading. So it's multi-graded coordinate ring. What does it mean? So this means that the degree of each alpha is equal to 1, 0, 0. This is multi-graded by k integers. Degree of each beta is 0, 1, 0, and of course so this is a multi-graded ring, and it corresponds, the way it corresponds to this tensor world is the following. If we write it as a sum, okay, so this S of X is a direct sum over all elements, maybe D inside Z to the K of the graded pieces. So this thing, each of those things is simply the degree D piece of this homogeneous ring. So the polynomials that are homogeneous of degree D1, D2, D2, D3, and so on. And this corresponds to, again, to this direct sum of the following symmetric product. Answer D1, so I should say that D is equal to D1 up to dk. Okay, so this is kind of like a dual space to what started over there. And maybe I should, at this point, I should be careful to explain why I use this bracket here and I don't use the brackets here. That's a little bit true. Well, it's not so much relevant if you are in characteristic 0, so if the base field is, for example, field of complex numbers. But in positive characteristic, this is a significant difference. So I should say that SdK in some vector space, let me call it V, is the space of polynomials, homogeneous polynomials of degree. Let's skip this index, while the bracket thing is the space of tensors, symmetric tensors. And in characteristic 0, these two things are isomorphic in all sorts of ways. But in positive characteristic, there is a difference. So let me illustrate it in the case that t equals 2. What's the difference? The difference is that, well, if we take S2V, this is in V tensor P, this is just, well, the set of, well, it's the set of all writings like this for all possible x and y's. Well, it's the linear span of, let me just do the case of V dimension of V is equal to 2, in which case this is correct. But this can be generalized. So in particular, x, that's incorrect. That's completely the opposite thing. I wanted to say. Let me fix this. Sorry. Okay, so this is the space of the tensors T, such that if you act with sigma, which switches the factors one through the other, you get the same T. So in particular, we have things like x times x here, obviously, but we also have things like x times y plus y times x. So these are the two different things that we can have here. And in characteristic 0, we can write this guy as a guy of this guy, or of this form, or in fact, in any characteristic different than 2. So if we take half of x times x plus x times x, which is the second one, then we get the first guy here. But in characteristic 2, this doesn't work. And it's in fact the case that we cannot write the first guy in the second form. So we really need two forms. And of course, if this is larger, then the other characteristics are also problematic. So in particular, for the symmetric tensors, we denote this guy as x squared with brackets, so it's a divided power. And this is because it's like really, well, it's equal, kind of equal of half of x times x. Okay, so this dot means just the naive thing you would guess. So you take a tensor x, and you tensor it with x with itself. So you get this thing, and it's and then you symmetrize it. So Is this clear, or should I explain it more? I'm not sure how have you ever seen this notation before or not? Not. Okay, so let me right. So the notation dot serves as notation for symmetric tensors or polynomials as well. If you have two different vectors, you take x and y, you multiply them. Well, what you would like to do, you would like to take this honest tensor, honest product, but now we are not in the symmetric case anymore. In general, if x is different than y, then you get something different, then it's not invariant under the involution. So what you usually do is you add the extra term. So you do exactly this operation. Right. So this is that. And if you plug x equal y, then you get this formula. So this bracket 2 square means precisely. Yeah, so I don't want to use halves because I want to be allowed to use any characteristics. But in any other characteristic than 2, this is correct. In characteristic 2, this is what it should be, but it's not. Right? And then that's why this guy here. So x bracket 2 is not equal x squared. So this guy I would denote x squared, except that it tends to be 0 in some cases.
Could you just, what is, so is one space smaller than the other?
So they are different. They are the same dimension, but they are different in the sense that they are different representations. If you try to change basis in V, then these changes of basis work completely different. Okay, so I just discussed the divided powers, the symmetric tensors, and let me just quickly explain what S to V. It's just a space of degree 2 polynomials. So then it becomes just the usual arithmetic that you are very well familiar with. So if you take x times x, you get, so for example, let me give you one example. If you try to do x plus y square, then this is just x square plus twice xy plus xy square, as you all were aware of that. And then if you look at this middle term, it vanishes in characteristic 2, so it now becomes much more simple. Whereas the divided power, so if you try the same thing here, this becomes x squared plus x dot y plus y squared. Right, so this guy does not vanish. This guy vanishes in characteristic 2. Okay. So that's why. Okay, and the tricky part is that if we take S d v and take the, well, maybe let me take dual here, and we take the dual of that. That's probably not the way I want. I want the other way around, I guess. No, that S d v. So these two spaces are dual representations of GLV. So if you try to, the way that you change basis on one side is the dual to like transpose of the way that you want to change the basis on the right hand side. Yes.
Can you define S to be without choosing a basis?
Yes, it's a space of the symmetric tensors of degree.
Yes, but the space of polynomials.
Oh, the space of polynomials, it's space of polynomials of degree 2.
Are you implicitly choosing a basis of B or?
You can prove that this is independent of the choice of basis. So if you choose a different basis, then you change the basis in S to V in the same way, and it's the same thing. You get the same thing with the respective action.
What's the main difference between the variables alpha, beta, and gamma?
Right. So so the variables alpha correspond to the space A1. The variables beta correspond to space A2, and variables gamma correspond to the last one. That's the. I mean, this is just the same, but they correspond to different tensor spaces. Right, so now, so I have this coordinate ring S of X, which is the direct sum of the SD 1A1 star as a product with SDK AK without brackets, but with star. And then I want to kind of define, well, I don't really care about the polynomial ring structure here, so I only look at it as a vector space, but this is a kind of dual of that, so-called graded dual. That's direct sum of the dual spaces. That. I added this twiddle to stress that this is different. I will, at some point, I will start skipping x. X is always the same thing here. But we have these two dual vector, well, they are not exactly dual vector spaces, but kind of graded dual things. And as always, in case the duality, we have some, well, one acts on the other. And the action I'm interested in is the following. If we take something from this polynomial ring, the first one, and act on the other one, we end up in, again, this tensor space. So in other words, so this guy here is like where our tensor lives, right? So our tensor that we started from lives in one of those homogeneous components of this guy here, and then the other one is something that should help us work with this tensor. But for that, we have this so-called apolarity action, which I will denote by little hook. And well, what it does is it takes something from here. Let me call this guy theta, and the tensor here, and it spits out another tensor, which is defined. So I will do, first I will do a formal definition on variables, then I will do an example. And the definition is that if I take any variable, so for example alpha, one of the alphas, and take the tensor t, then this the result of this this action is, what you do is you, well, it's a contraction action. So it's what you do is, if this was in characteristic 0, if this were honest polynomials, what you will do, you would take the derivative with respect to the first coordinate of t, but this is divided power action. So this means that you take the derivative, but in a very naive way, like if you didn't know that the derivative of a polynomial has a constant. Again, it's the same feature as over there. So, and the same thing happens on all coordinates. So the betas will act on the second. So if this guy here was in as d1 and so as dk, then this, and I took just degree 1, 0, 0, 0 guy, then this guy will live in as d1 minus 1, a1. I only reduced the degree in the first coordinate and left all the others invariant. Then you extend this action linearly, and then you extend this action in a way that a decent polynomial ring should act. So let me give you an example. If theta is equal to, I don't know, alpha 1 square minus beta 2 square, 1 square, something like that. And t is a tensor that I would write as x1. x1 is the coordinate that's dual to alpha 1. Something like that, maybe. I added all the brackets. So this is in S5 of some vector space whose one of the elements is x1, and the x1 is dual to alpha 1. And then what I do is I act with those two guys linearly. First, I take the derivative the contraction with respect to x1. So theta hook t is just alpha 1 square hook t minus beta 1 square hook t. And this thing becomes, well, what I do with derivative, if I take the derivative of x with respect to x, what I simply reduce the power, and since I'm divided power, I don't need to take care of the constant, so this is equal to x1 cube tensor, the same thing as here, and then this guy here, on the other hand, is minus x1 to the 5th tensor. Well, I have to derive this guy twice with respect to y1. So this guy becomes y1, and then this guy becomes y2. And there are no constants here. So this is the apolarity action. It's very useful in practice. It's also algorithmically well. It's easy to define it algorithmically. Yes, sorry.
Can you define it and on a video basis?
Yes, but I don't want to do it here. I mean, you know it better than how to do it. Well, so first of all, I would need to properly define the coordinate system. So instead of starting from a tensor space, I should have started from the polynomial ring. So if I take S of x, then I produce the dual of this. So the linear homomorphism of this into K, and this is equal to the divided power polynomial ring, and not polynomial ring, the power series ring. The power series ring, which contains the polynomial ring in the same variables, divided powers. And this is invariant now, subject to this guy. This guy is defined invariantly as a direct sum of symmetric powers, and so on. So there is a way of doing this, but I don't want to go into there. In coordinates, this is probably the way to explain it. So the reason I mention this is because of the following apolarity theorem. So whenever I have a decomposition of T into a sum of simple tensors, so I would write this T, this tensor T as a sum of tensors Pi, with each Pi being a simple tensor of multi-degree D1, D2, D, and so on. Then what I can do two things. One thing is take the annihilator of T. It lives inside S of X. So remember, this guy here is a subset of this S twiddle in some degree D. And I'm going to define two objects inside of the other one, of those. Yes?
A question on your example here. Should we think of x1 to the power of 5 in brackets as essentially x1 to the 5, as normal power divided by 5 factorial?
Yes, if you are in large characteristic, yes. Yes, and then the derivative language works out well. So the annihilator is just simply the set of all those thetas in Sx, such that this is 0. All those guys that kill T with respect when you take the apolarity action. And the other, this is a subset of S of X, and this is in fact an ideal, meaning that first of all it's a linear space. So if you take two of these guys that annihilate, then this is a linear action. So it will also the sum or the linear combination will also annihilate. And then the second of all, if you take theta times psi in the annihilator, or theta and psi in the annihilator of T, then theta times psi hook T is equal to the same thing as theta hook psi hook T, which is theta hook 0. Actually, even you don't need this. You take arbitrary theta and psi in the annihilator, and then this is already 0. Therefore, this guy here is in the annihilator. So it's an ideal. And moreover, the second ideal that I want to construct is the ideal of the points. And this is going to be a multi-homogeneous ideal. And And the multi-homogeneous ideal is defined, well, it's generated by all those theta that are as x, and they are homogeneous for some degree, maybe not the same degree as p leaves, like d prime, for some degree, and they vanish on p, on pi's, meaning that theta will, right, so I should be very careful here. So theta of pi is equal to 0, and I should explain what this means. So this can be interpreted in the two different ways. What is this thing? First of all, we can think of pi as a point in this multi-projective space, PA1. Remember, this is our x. And then this is just taking my thinking of theta as a coordinate function on those multi-projective spaces. So you just check if all your coordinates vanish, if the functions that if you evaluate it at pi, if they all vanish. So that's one way of thinking. And if you don't like this, because it's kind of algebraic, geometric way of thinking, you may prefer to think about it in a slightly different way. So if you take pi, this is in x, so or x hat. This is some x1 to some power d1, so xk to some power dk. This is in this tensor space as twiddle of x. So you produce a slightly different version of p. Let me call it pi to d prime in degree d prime in this other degree, which will be the same thing, except I use different degrees. So you reinterpret your point as a tensor of completely different degrees. And then this theta of pi is equal to 0, if and only if. You can take it as a definition. If and only if theta hook pi d prime is equal to 0. So you can reinterpret it in the other way. So these two interpretations are equivalent, and they are both algorithmic. So if you are given explicit example, you can just plug it into computer and see if one or the other holds, whichever you prefer. And the relation between this and that is the following statement. Now I have to switch. So the plane apolarity lemma is the following. equivalence, so we can say that T can be written as a direct sum of simple tensors, P1, PR, perhaps with some constants. Let me call them lambda 1 up to lambda r, if and only if the ideal of P1, PR, so the second thing, is contained in the annihilator of T. So there exists constant lambda 1 up to lambda r, such that this T can be written as a sum of this. And we can read it in the following way. So this ideal here is, this guy here is always radical. It has the property of being saturated with respect to the alpha 1, alpha D1, not alpha 1, alpha A1, and with respect to beta 1 up to beta A2, and so on. So I don't really want to explain in details what this means. It's an algebraic operation that you can verify. And also this, the fact that it's an ideal of R distinct points, let's just assume that P1 is not equal to mu Pi, is not equal to mu Pj, so there are really different non-proportional points on X. Then the dimension, the codimension of I of S of X divided by I in degree d prime for d prime very large is always equal to this number R, so the number of points. So you can rephrase this that if you're familiar with the notion of rank, well, in this case it's partially symmetric rank of T is less or equal to R, if and only if there exists an ideal like this. So if and only if there exists I, which is, well, it's an ideal in Sx, which is multi-homogeneous, radical, saturated with respect to the same guys, having this codimension, and finally, the important condition which relates it to T, this annihilator of T contains I. Well, so the way, so this is a quite complicated phrasement of this, but the way we use it is to, well, we take the reverse implication. So we typically we do not show in this way the upper bound on T, on the rank of T, but we show the lower bounds on T. So this means that we prove that if there, well, we take a tensor that we like, and we want to prove that its rank is large for some reason. So we tried to find a small ideal, well, the large ideal, the one that has small value of R here, and has all those properties, and then we prove it doesn't exist. And this is again a little bit tricky, doesn't always work, but there are many examples in the literature where this actually proved to be effective. Okay, and then instead what, so this thing is kind of classical, but the new thing is the border version of that. Instead of rank, we want to use the border rank.
Have you explained why for apolarity, the apolarity statement, why there is this equivalence?
This one.
Yes.
I could do that, but maybe afterwards. It's a simple argument. It will require 5 minutes or 10 minutes to write it up. So the next thing is the border apolarity. So the border apolarity corresponds to secant varieties. So it's again a subset of the same space of tensors in some degree D. But instead of only considering the tensors that can be written as P1 as PR for Pi in X, and a simple, as a combination of simple tensors, we take the closure of this set. Well, you can ask in which topology. Well, if you are over complex numbers, then this is just Euclidean topology is good enough. And in general, I'm using Zariski topology, whatever that is. But it's kind of a way of phrasing both points of rank R, or at most R, and their limits. Classical example is so-called W state, which has typically has higher rank than border rank, meaning that it actually is in a small secant variety, but it doesn't have a small short expression like that. And then this closure here is something that makes a lot of people sleepless. And it's very difficult to decide whether a point is in a closure of given set or not, in general. And that's why we were struggling to understand this set. And the result is the following theorem, is that if we have T in secant variety of X, if and only if there exists an ideal inside S of X, which is again multi-homogeneous, and it has dimension, the correct dimension, well, it's almost always equal to R, except when it's not possible. It's minimum between this and the dimension of Sx in degree d prime. So in cases, this is like a the space of homogeneous polynomials of fixed degree is very small, smaller than your number R, then this thing kicks in and you have to use this one. You cannot have ideal, so even if you took 0 in this degree, then you wouldn't get precisely R. You always get something less than R. And then, well, the important condition is the annihilator of I is contained. in S of X, and then the life would be beautiful if this was so. But unfortunately, there is one more condition, which is the most difficult one, that I is a limit of ideals.
You don't know annihilator of Sx, but annihilator of T.
Annihilator of T, sorry. That's a mess. Thank you. It's a limit of ideals of points. So ideals of points are guys like this. And then we want to take this as a limit. Okay, so it doesn't, well, so on one hand it's an if and only if condition, so it seems like on this side we got rid of the closure. We had the closure here, but we kind of got rid of it. Except this last condition is a version of a closure, right? Because it also says about limit. And that's not so good. So what we do instead, if we want to prove, well, so there are two things. So if we want to prove a lower bound on this R, so we want to prove that T is not in some secant variety. This has higher border rank. It's more complicated than just a limit of R simple tensors. Then what we do is we try to find this ideal, and we forget this last condition. So we only try to prove that there is no ideal with these first properties. And this is closed thing, and this is an algebraic verification that sometimes, if you are lucky, possible. So that's one option. Second option is try to understand this thing, and this is being done by Manjuk and his friends, also partially by Yelisheyev. I mean, Yelisheyev does a lot of things, but also had some contribution to that, and more people is working on that. But in these talks, I will only use the weaker version without this last thing. This and the talk tomorrow. I won't discuss these results of Manjuk and others. So the idea is that you replace the condition on T with the border rank of T with some hardcore algebra thing that actually can be verified in some cases. So one last thing I want to say is the following, and then I will give examples in the next talk tomorrow. First,
So when you say I is a limit of ideas,
what's the question?
yes, what do you mean?
What do I mean? Right, so that's a very good question. It's there is a space of all homogeneous ideals with given, so this thing here, the dimension of, well, codimension of an ideal in each degree is called Hilbert function. So dimension of S of X modulo I in degree D prime. It's a property of ideal, of a multi-homogeneous ideal, and it's called Hilbert function. And if you take the set of all homogeneous ideals multi-homogeneous ideals with prescribed Hilbert function, some fixed function h, then this thing is called Hilbert scheme, multigraded Hilbert scheme of ideals with this Hilbert function. That's the name. And then for each, whatever h you take, in particular this one, this is projective variety, projective scheme. But if we are only talking about the set structure, it can be reducible, so not really a variety in a strict sense, but projective variety in some projective space, a closed subset of projective space, Zariski closed. And inside here, there is a component, irreducible component, which, well, if you take this particular Hilbert function, then you can find the slip variety here inside this, which corresponds to precisely those limits of ideals of points. So what you take the set of ideals of points and take its closure. So what I did, I moved the problem of closure from one place to another, but along the way, I've gained some conditions. So,
When you say isolimit, it means that the variety is smoothable.
it's a little bit more tricky. So there is no variety. I did not say about the variety. You could be thinking about schemes, but I don't really want to think about schemes here. That's not enough. I mean, just the fact that this underlying scheme of I is smoothable is not enough for the ideal to be in this slip. It's a stronger condition, which says kind of that ideal is smoothable. The ideal is itself smoothable. So it is a limit of the ideals of points. It's slightly stronger. That's why there is difference between this and what was known before. It's subtle, but strong.
So it's not that you take some flat family and...
You take a flat family, but not of schemes, of the ideals. So the problem with schemes, or even with points, is that if you take 3 points in general position in the tensor space, and you move one of them into a line that's spanned over them, what you get is that if you take the limit of the linear span of R, so this T is a parameter which you converge to, say, 0 or something, and you take the linear span of these points, so a linear combination of those, then this contains the linear span of the limit, but in this example shows it doesn't always equal, right? So because in general you get the plane, you take the limit, you still get the same plane, but the linear span of just 3 points is less. So to work with ideals instead of to work with the schemes is a resolution of this problem, where if I replace it by correct like linear span of an ideal, then this becomes honest equality. And that's why it's good to take the limits of ideals. What else? So I wanted to state the invariant version, but maybe I will leave it for tomorrow.
Thank you very much. Are there questions?
Please.
Yes, you received the result about the
that I said that the makes the, what do you refer to as the name sleep, or you were? This thing. I mean, this is just definition. The theorem is here. I'm not sure what was the question. So the theorem. So the secant variety is a subset of those tensors. So this, remember, this is just this tensor space W I started with. And yeah.
So I wanted to ask, so would it be the same to smoothability if I was saturated?
I was saturated. Yes, if you take I saturated, then this would mean that the, well, so if I was saturated and a limit of ideals of points, then this underlying scheme would indeed be smoothable. I mean, in general, the underlying scheme is always smoothable, but the converse implication is not true. I mean, you can have. So the thing is that the good thing about this is that you have single Hilbert function, which is kind of the Hilbert function of general points. I mean, it kind of excludes these guys from the, it replaces each of those guys with all possible limits that of the linear spans that we can get.
I would guess that in this case, your I, the one that you would get, would not be saturated.
Exactly.
Any questions appear to be why? If not, let's thank Jarek.
Thank you.